In Russia's Far East, where Pacific storms and drifting sea ice challenge every structure built along the coast, a colossal bridge rises across a narrow strait. This is the Russky Bridge. With a main span of 1,104 meters, it was once the longest cable-stayed bridge span in the world. The structure features a steel deck, 320-meter-tall A-shaped reinforced concrete pylons, and was completed in just 40 months despite the region's harsh construction conditions. In this video, join Mandarin Tech as we explore how Russia built one of the most remarkable cable-stayed bridges ever constructed. Located in Vladivostok, the largest administrative and economic center of Russia's Far East, the Russky Bridge spans the eastern Bosphorus Strait, connecting the Nazimov Peninsula on the mainland to Russky Island south of the city. Construction began in 2008 and was completed in 2012 at a cost of nearly $1 billion. The bridge was built as a key project to support the Asia-Pacific Economic Cooperation APEC Summit, while also serving as a strategic infrastructure investment aimed at promoting the long-term development of Russky Island and the wider Far Eastern region. The bridge provides a clearance of approximately 70 meters beneath its 25-meter-wide deck, which carries 4 lanes of traffic. The structure is supported by 168 parallel stay cables and is equipped with damping systems to ensure stability in this seismically active area. Before the first foundation piles were drilled into the seabed of the eastern Bosphorus Strait, the area where the bridge would rise had almost no infrastructure capable of supporting a world-class engineering project. To overcome this challenge, 2 large construction bases were built at opposite ends of the future bridge. These facilities functioned like miniature industrial cities, equipped with everything needed to support thousands of engineers and workers. At the heart of each base were modern concrete batching plants, supplying a steady flow of concrete for construction activities on both sides of the strait. Surrounding them were mechanical workshops, maintenance facilities, worker accommodations, and large dining halls. Most of the steel and concrete components required for the project were prepared and assembled here before being transported to the construction. At the same time, an entirely new logistics network was developed. Temporary ports, material storage yards, and massive assembly areas gradually appeared along both shores of the strait. To support the project, more than 320 specialized machines and pieces of equipment were mobilized to the site. Within just a few months, the once quiet shores of the eastern Bosphorus Strait had been transformed into a gigantic construction hub operating around the clock. Once the massive logistics system was fully operational, construction moved into its first major phase, building the approach structures that would connect the future bridge to both sides of the strait. Engineers constructed 2 approach viaducts with a combined length of more than 900 meters. Along these routes stood a series of bridge piers reaching heights of up to 30 meters, carefully positioned to follow the natural terrain on both shores. Each pier was precisely engineered to ensure long-term structural stability and load-bearing capacity. Above the piers, crews assembled a composite steel and concrete superstructure. Inclined steel box girders were installed first, forming the primary load-bearing framework of the bridge. Once the steel structure was in place, reinforced concrete deck slabs were cast in situ, tying the entire system together into a single integrated structure. This design provided high structural strength while reducing the overall weight of the bridge, an important advantage for a project of this scale. The next stage focused on constructing the foundations for the bridge's 2 massive pylons in the middle of the strait. On the Nazimov Peninsula side, engineers created a rock-filled artificial island to support the foundation works. Hundreds of thousands of cubic meters of rock were transported to the site and continuously dumped into the sea, forming a stable platform for large-scale piling equipment. On the Russky Island side, construction began with a temporary offshore steel island before a protected artificial peninsula was built around the future foundation area. Once these construction platforms were completed, piling operations began. Each bridge tower was supported by 120 drilled shafts, each measuring 2 meters in diameter. Engineers then constructed enormous pile caps designed to connect the entire pile system and transfer the loads of the pylons into the ground below. Each foundation consumed approximately 20,000 cubic meters of concrete and nearly 3,000 tons of structural steel, making it one of the largest bridge foundation projects ever undertaken in Russia. After months of work amid strong winds, rough seas, and winter ice, the two gigantic foundations gradually emerged from the waters of the eastern Bosphorus Strait. With the massive offshore foundations completed, the project moved into an even more impressive phase, constructing the two bridge pylons that would rise more than 320 meters above the sea. For a cable-stayed bridge, the pylons are the heart of the entire structure. Each tower was designed as an A-shaped reinforced concrete pylon. This was not only an architectural choice, but also a critical engineering solution. The A-shape helps distribute the forces from the stay cables more efficiently into the foundation, while providing greater stability against the powerful winds that frequently sweep through the strait. Surrounding each tower was a giant self-climbing formwork system consisting of 7 working levels with a total height of 19 meters. After each concrete pour, the entire structure was lifted upward by hydraulic modules, allowing construction to continue on the next section. The process operated like a vertical assembly line. The scale of the work was enormous. Each pylon consumed more than 20 cubic meters of high-strength concrete and thousands of tons of reinforcing steel. As the towers climbed higher, new challenges emerged. At elevations above 300 meters, strong winds could cause significant crane movement and increase the risk of instability during lifting operations. During periods of severe weather, many installation activities had to be temporarily suspended to ensure worker safety. After months of continuous construction over open water, the two giant pylons finally reached their full height of 324 meters, roughly equivalent to an 80-story building. They became the tallest concrete structures ever built in Russia's Far East. While the A-shaped pylons continued rising above the skyline of Vladivostok, another massive undertaking was taking place at ground level: the fabrication of the bridge's steel stiffening girder. For the Russky Bridge, the stiffening girder is far more than just the roadway carrying traffic. Engineers selected a closed steel box girder design with exceptionally high torsional rigidity. From the outside, the structure resembles a giant steel box stretching continuously between the two pylons. Inside, a dense network of transverse diaphragms and reinforcing steel plates provides additional strength while keeping the overall weight as low as possible. The bridge's steel girder system extends for approximately 220 meters and was divided into 103 individual steel panels. Each panel measures about 12 meters in length, 26 meters in width, and weighs hundreds of tons. Combined, the entire girder system contains roughly 23,000 tons of steel, comparable to the displacement of several modern destroyers. Rather than fabricating the sections directly on site, most of the panels were manufactured in controlled factory conditions to achieve the highest possible level of precision. Once completed, the panels were transported to an assembly yard on the Nazimov Peninsula. There, engineers pre-assembled multiple sections into larger modules before moving them to the construction site. This prefabrication strategy provided major advantages. If every alignment and welding operation had been performed high above the water in the strait's strong winds, construction would have taken far longer and involved significantly greater risks. By completing most of the work at ground level, engineers were able to reduce both construction time and the amount of high-altitude work required over the sea. After more than 23,000 tons of steel box girders had been fabricated and pre-assembled, the project entered what many considered the most spectacular phase of construction, lifting these enormous steel sections more than 70 meters above the strait. From the water below, individual panels were hoisted to a height of 76 meters using derrick cranes with lifting capacities of up to 400 tons. Working from both sides of the strait, the steel deck gradually extended outward from the bridge pylons. After each lift, engineers carefully checked the alignment, elevation, and geometry of the structure before carrying out the final welding operations. Any deviation, no matter how small, was identified and corrected immediately before the next section was installed. The amount of welding required was immense, with the total length of welded joints exceeding 30 kilometers. For months, the construction site operated almost around the clock. Thousands of tons of steel were continuously transported, lifted into position, and permanently connected, gradually transforming individual components into a single continuous bridge deck stretching across the eastern Bosphorus Strait. As the steel deck gradually extended from both sides of the strait, the bridge was still unable to support itself. To transform the massive steel structure into a complete bridge, engineers had to install the stay cable system, the most critical component of the entire project. For the Russky Bridge, the stay cable system was built on a scale never before seen in cable-stayed bridge construction at the time. The cables weighed approximately 3,720 tons in total and had a combined length of 54 kilometers. Each stay cable consisted of bundles of parallel steel strands. Every strand contained 7 high-strength galvanized steel wires designed to resist corrosion. Surrounding the cables was a high-density PE protective sheath that shielded them from salt spray, moisture, and the harsh marine environment of Russia's Far East. Installation began at the anchor points near the tops of the pylons. The cable bundles were gradually extended down to predetermined locations along the steel deck. As each new cable was tensioned, the loads within the structure were immediately redistributed, bringing the bridge closer to its final load-bearing condition. Beyond carrying enormous structural loads, stay cables were specifically engineered to withstand strong winds. Engineers adopted a high-density cable arrangement that reduced the overall cable diameter, helping to decrease wind loads on the structure by as much as 30%. The outer ledge-deep sheathing also featured special helical ribs running along the length of each cable. These ribs disrupted airflow and rainwater flow around the cables, reducing wind and rain-induced vibrations that could otherwise affect the bridge's stability. Over many months, dozens of kilometers of stay cables were installed and precisely tensioned. With each new cable, the bridge became more stable and gradually took on its final iconic form. After the final stay cables had been tensioned and the full load of the main span had been transferred to the 2 A-shaped pylons, the Russky Bridge finally emerged in its complete form. Attention then shifted to finishing the bridge deck in preparation for operation. On top of the massive steel girder system, engineers installed multiple layers of specialized roadway structures to create a durable and stable driving surface. As the deck gradually took shape, the bridge's final appearance became increasingly clear. Along the entire route, safety barriers and guardrails were installed to protect vehicles traveling more than 70 meters above the sea. Lighting systems and various monitoring devices were also integrated into the structure, allowing engineers to continuously track the bridge's condition after it entered service. These finishing works were carried out simultaneously along more than 3 kilometers of bridge, transforming the giant steel structure into a modern transportation link capable of handling tens of thousands of vehicles each day. Once construction was complete, the bridge entered the load testing phase. Convoys of heavy trucks were driven across the deck to simulate real operating conditions. Meanwhile, schedule pressure remained intense. Thousands of workers, engineers, and specialists continued working around the clock to complete the final details. Every component, from the pylons and stay cables to the steel deck and roadway surface, was thoroughly inspected before the bridge was approved for full operation. Originally built to support the 2012 Asia-Pacific Economic Cooperation, APEC Summit, the Russky Bridge has become far more than a connection between the mainland and Russky Island. It stands as a symbol of a new era for Vladivostok and a reminder that even in some of the harshest environments on Earth, engineering can overcome extraordinary challenges. Today, the bridge remains one of the most remarkable cable-stayed bridges ever constructed, combining record-breaking scale with innovative engineering solutions. Do you see the Russky Bridge as a true engineering marvel, or as a strategic project designed to strengthen Russia's presence in the Asia-Pacific region? Share your thoughts in the comments below. And don't forget to subscribe to Mandarin Tech for more incredible engineering stories and mega projects from around the world.